Good morning, dear students and friends. I again welcome you in the lecture series of the subject that is a 303 106 103. It is a triple E subject. We are discussing the chapter number 1, that is a DC circuits, and we are solving the sums of a various theorems. So this is the lecture number 3, and in this lecture we will solve the sum using the superposition theorem. So this is the circuit diagram. This is the same sum. It means same problem statement which we had used by solving the sum using a Thevenin's theorem and Norton's theorem. So we are interested in finding the current through the load resistance, that is RL is equal to 1 ohm, which is connected between node A and node B, and the rest network is same. Now in superposition theorem we know that the circuit contains more than one energy sources. In this circuit it contains two energy sources, two voltage sources, that are 3 volt and 1 volt, right? So in superposition theorem at a time we apply only one energy source and we find the response. Response means we find the current through the various elements. Then in step number 2, yes, in step number 1 we apply only one energy source, and at the same time other energy sources are represented by their respective internal resistances. So right, so if there is a voltage source and it has some internal resistance, then that voltage source is replaced by its internal resistance. And if in most of the cases we assume that the internal resistance of the energy source is 0, right, and if it is a voltage source, then voltage source is replaced by the short circuit. And if there is a current source, then current source is replaced by the open circuit, right? So at a time we apply only one energy source and we find the response, it means current. Then in step number 2, in this case we will apply 1 volt energy source. At the same time this 3 volt energy source will be represented at the short circuit, at the source as the short circuit, and again it means we will find the response, it means current through the 1 ohm resistance, right? And finally, to get the overall response, to get the resultant current through this 1 ohm resistance, we will take the algebraic addition of the current which is obtained by using only 3 volt energy source and by using only 1 volt energy source, and we will take the algebraic addition of the currents obtained by this energy source as well as this energy source. So we will obtain the resultant current. So this is all about the superposition theorem, right? So now let's see the step number 1. First we apply only 3 volt energy source and we make other energy source is 0. So in this case there is a 1 volt energy source, so it's a battery, it is a voltage source, so voltage source is represented as the short circuit. So now draw the equivalent circuit. So 1 volt is represented as short circuit, remaining circuit remains same. Now remember, in a superposition theorem we are not removing the load resistance. Load resistance is kept as it is in the circuit diagram. So it is connected between node A and B. So this is the equivalent circuit when only 3 volt energy source exists in the circuit. Now we are interested in finding the current through the 1 ohm resistance. So yes, you can apply mesh analysis, nodal analysis, etc. Now yes, there are 3 meshes. This is mesh number 1, A, C, D, A. There is a mesh number 2 C, B, D, C, and there is a mesh number 3 A, then 1 ohm resistance, then B, 2 ohm resistance, C, 2 ohm resistance, A. So A, 1 ohm, B, C, A. This is the third mesh. So you can write the three mesh current equations, right? See, in lecture number 2 we had written three mesh current equations. Just similar to that, you can write three mesh current equations, or you can simplify the network. And if you simplify the network, then the equations will reduce, so there will be less computational burden. So again, see, in this case you can see that node C and D both are same nodes because those are shorted. So we can now draw the equivalent reduced circuit diagram. So again, first of all, place the principal node, and principal nodes are A, B, C and D both are same. So now this circuit contains only three principal nodes, A, B, C and D. So first of all, place the principal nodes. Now one by one connect the resistance. So between A and C, 2 ohm resistance. Between A and D, 3 ohm resistance in series with 3 volt source. 3 ohm in series with 3 volt source. Then between B and D, 2 ohm. B and D, 2 ohm. B and C, 2 ohm. B and C, 2 ohm. And between A and B, 1 ohm. A and B, 1 ohm. Now you can see that these 2 ohm resistance and this 2 ohm resistance are connected between the same principal nodes. Those are B node and C node, right? So see, the one end of this 2 ohm resistance and this 2 ohm resistance is connected between node C, and this other terminal of this 2 ohm and this 2 ohm are connected with B. So both the resistances are connected between the same principal nodes B and C. So as per the definition of parallel connection, we can say that this resistance and this resistance are connected in parallel. So its equivalent is 2 into 2 upon 2 plus 2. So it is 1 ohm. So you can again draw the reduced equivalent circuit diagram. So first of all, locate the principal node. A, B, C and D both are same. So between C and B, equivalent is 1 ohm. So this is 1 ohm. Between A and B, it is 1 ohm. 1 ohm. And then between A and C, 2 ohm and 3 ohm and 3 volt, right? This. Now notice one point. These 2 ohm resistance and these 3 ohm resistances are not connected in parallel. Why? It is because the one terminal of 2 ohm resistance is connected between node A. The one terminal of 3 ohm resistance is connected to node A. Yes, that is okay. But what about the other terminal? The other terminal of 2 ohm resistance is connected to the C terminal, whereas the other terminal of 3 ohm resistance is connected to the positive of the battery, 3 volt battery. So other terminal is not connected to the C terminal, right? So see, you can see that the two resistances are connected in parallel if and only if they are connected between the same two principal nodes. If the terminals starting and finishing end are connected with the same two principal nodes, then only we can say that those resistances are connected in parallel, right? So these 2 ohm and 3 ohm are not connected in parallel. Please see this fact. So now you cannot further reduce this circuit diagram. So yes, now there are two meshes, so apply the mesh current equations. So this is the first mesh, which consists of 2 ohm, 3 volt source and 3 ohm resistance. This is the second mesh, A, B, C, A, which consists of 1 ohm, this 1 ohm and 2 ohm resistances, right? So see, originally the circuit consisted of 3 meshes, 1, 2 and 3. After simplifying the network reduces to 2 meshes, mesh number 1 and 2. So there will be only 2 equations to be solved, right? So write down the mesh current equations for the first mesh, right? So I say that the current in first mesh is I1 dash and current in second mesh is I2 dash. So the generalized equation is R11 I1 dash plus or minus R12 I2 dash is equal to plus or minus V1. R11 is the sum of the resistances in first mesh, so it is 3 plus 2, it is 5 I1 dash plus or minus R12, sum of the resistances common to first mesh and second mesh, and it is 2 ohm. So it is a 2 I2 dash. Now plus minus. So again consider the common resistance. Through the common resistance of 2 ohm, 2 currents are flowing. It is I1 dash, it is flowing from A to C, and I2 dash. I2 dash is flowing from C to A. So the direction of I1 dash and I2 dash are opposite to each other. So we put the negative sign. So we put minus 2 I2 dash, and it is equal to plus or minus V1, sum of the algebraic sum of the voltages in the first mesh. There is only one energy source, 3 volt. So if there is only 3 volt, then it will supply the current from positive to 3 ohm to A to 2 ohm to C to negative and then to positive. So it supplies the current in clockwise direction, and the assumed direction of I1 dash is also clockwise. So both the directions are clockwise, both the directions are same. So we put positive voltage. So we consider positive 3 volt, right? So equation number 10 is 5 I1 dash minus 2 I2 dash is equal to 3. Now we write the mesh current equation for mesh number 2. So it is plus or minus R21 I1 dash plus R22 I2 dash. This is main diagonal, so it is always plus. It is equal to plus or minus V2. Now recall that R21 and R12 both are same. So it is minus 2 I1 dash plus R22, sum of the resistances in second mesh. So 1 plus 1, 2, 2 plus 2, 4. 4 I2 dash is equal to plus or minus V2, sum of the voltages in second mesh. No, there is no voltage source, so V2 is 0. So equation number 11. Now solve equation number 10 and 11. You obtain I1 dash as 0.75 amps, I2 dash 0.375 amps, right? And we are interested in finding the current through load resistance, and load resistance is of 1 ohm, which is connected between A and B, right? So which current is flowing through A in 1 ohm resistance? It is I2 dash, and we got the positive answer of I2 dash. It means current is flowing from, so assumed direction is correct. So actual direction is same as that of assumed direction. So actual direction is also clockwise. So as far as branch AB is concerned, current is flowing from A to B. So current is flowing from A to B through 1 ohm resistance. So the response, it means current through the load resistance RL, that is equal to 1 ohm, is I2 dash is 0.375 if we apply only one energy source, and that is of 3 volt. So step number 1 is complete. Now step number 2, now apply the other energy source. and other energy source is 1 volt. Now apply only 1 volt and make other energy source is 0. In this case there is a 3 volt source, so it is a voltage source, so short it. So voltage source is shorted, remaining circuit remains as it is, right? So now again there is node A, C, B and D. Now see, node C and D are different nodes because there is a voltage source between node C and D. So the potential of node C and D are different. So in this case you cannot reduce the network further. So yes, there are 3 meshes: mesh A, C, D, A, mesh number 2 C, B, D, C, mesh number 3 A, then 1 ohm, B, 2 ohm, C, 2 ohm, A. So 3 meshes. Assume the direction of currents in each mesh. So I assume that in first mesh current is flowing, which is I1 double dash, and its direction is anti-clockwise. You can also assume clockwise, no problem. In mesh number 2, I assume the direction of current as clockwise and current is flowing is I2 double dash. And in mesh number 3, current I3 double dash is flowing in clockwise direction. So now apply the 3 mesh current equations. So mesh number 1, R11 I1 double dash plus or minus R12 I2 double dash plus or minus R13 I3 double dash is equal to plus or minus V1. Now R11, sum of the resistance is in first mesh, so it is 3 plus 2, it is 5 I1 double dash. Then R12, sum of the resistance is common to first and second mesh, there is no resistance, so it is 0 I2 double dash plus or minus R13. R13, sum of the resistance is common to first and third mesh, so it is 2 I3 double dash. Now plus k minus, again consider the common resistance between first and third mesh, so it is 2 ohm. Through the 2 ohm, I1 double dash is flowing from C to A, I3 double dash is flowing from C to A, so both the directions are same through 2 ohm resistance. So as both the directions are same, we put positive sign. So positive 2 I3 dash double dash, it is equal to plus or minus V1. So in first mesh it consists of only one source and it is 1 volt. Now positive and negative. If there is only 1 volt source, then current will be flowing through positive to C, C to A to D, D back to negative. So it flows in anti-clockwise direction, and the direction of I1 double dash is also anti-clockwise. So both the directions are same. That's why we put positive sign, positive 1 volt. So this is the equation number 12. Now write down the mesh current equations for mesh number 2. Plus or minus R21 I1 double dash plus R22 I2 double dash plus or minus R32 I3 double dash is equal to plus or minus V2. Now R21 and R12 both are same, so it is 0 I1 double dash plus R22, sum of the resistances in a second mesh, so it is 2 plus 2, it is 4 I2 double dash plus or minus R23, sum of the resistance is common to second mesh and third mesh, so it is 2. So it is 2 I3 double dash. Now plus k minus. Again consider this common resistance. Through this common resistance, I2 double dash is flowing in downward direction from C to B. And through this 2 ohm resistance, I3 double dash is flowing in upward direction from B to C. So the direction of I2 double dash and I3 double dash are opposite to each other. So we will put negative sign. So we put negative to I3 double dash. So it is negative. And it is equal to plus or minus V2. Second mesh. Now for this 1 volt source, the current will flow from positive to C, C to B, B to D and back to negative. Current will be flowing in clockwise direction. And the direction of second mesh current, that is I2 double dash, is also clockwise. So both the directions are same. So we put the positive voltage source. We consider positive value of the voltage source. So it is plus 1 volt. Now apply the mesh current equation for the mesh number 3. So it is plus or minus R31 I1 double dash plus or minus R32 I2 double dash plus R33 I3 double dash is equal to plus or minus V3. Now R31 and R13 both are same with sign. So it is 2 plus 2 I1 double dash. Then R32 and R23 both are same. So it is minus 2. Right? Consider the sign also. So minus 2 I2 double dash plus, this is the main diagonal, so always plus. Sum of the resistances in third mesh, mesh number 3. So it is 1 plus 2. So 3, 3 plus 2, 5 I3 double dash. It is equal to plus or minus V3. Sum of the voltages in third mesh. There is no voltage source, so it is 0. It is 0. So equation number 14. Now there are three equations. Equation number 12, 13 and 14. There are three variables, I1 double dash, I2 double dash, I3 double dash. Use the matrix, invert the matrix and get the solution. So I1 double dash is 0.1875, I2 double dash 0.2656 amps, I3 double dash 0.0312 amps. Now in which current we are interested? Try to answer. We are interested in finding the current through this 1 ohm load resistance, and current through 1 ohm load resistance is I3 double dash. So and we got the positive value of the I3 double dash. It means our assumed direction is correct. Actual direction is same as that of assumed direction, and assumed direction is what? It is clockwise. As far as 1 ohm is concerned, it is in downward direction, right? Current is flowing from A to B in downward direction, right? So current through load resistance is I3 double dash if you apply only one energy source, and in this case it is 1 volt energy source, this 1 volt energy source. And its magnitude is 0.0312 amps, and direction, always indicate the direction, it is downward. In this figure I have also indicated, this is 1 ohm, I3 double dash is flowing in downward direction from A to B, and this is the magnitude, right? So this step is complete. So now what we had done so far, we had at a time apply one energy source and we got the response. Then we apply another energy source and we get the response, right? So one by one we apply one energy source and at a time, right? So now there were only two energy sources, so steps are complete. Now in step number 3, take the algebraic additions of the responses which have been obtained by applying the one energy source at a time, right? So step number 3, resultant current. Current by applying both the individual energy sources. So resultant current through the load resistance, that is IL, it is equal to what? Current through the load resistance when we apply only 3 volt energy source plus current through the load resistance when only 1 volt energy source, 1 volt battery was applied, right? So IL, resultant current IL is what? This is I2 dash when we apply only 3 volt source. and its direction was from A to B. And current through RL, when we applied only 1 volt source, at that time current was I3 double dash and the direction was from A to B. Both the directions are same, so we put a positive sign. If the directions were different, then we would have been put the negative sign. So IL is equal to 0.375 plus 0.0312 amps. So this plus this will give you IL is equal to 0.4062 amps and direction is from A to B. So this is the answer, right? So notice one point. Answer obtained by the Thevenin's theorem, Norton's theorem and superposition theorem are always same, right? We got the same answer, right? So this is the answer. Okay, so yes, superposition theorem is very much useful in obtaining the current, and once you obtain the current, you can obtain the voltage, right, by multiplying this current by the resistance value. So you can obtain the voltage also, right? So superposition theorem can be applied to the linear networks, right? So in linear networks, there is a linear relationship between the voltage and current, but superposition theorem cannot be applied to the non-linear network, right? So we cannot determine the power, because power is what? Power is equal to I square R. So power is a quadratic quantity. It's a non-linear. Rather, it is a non-linear quantity, right? It is a quadratic non-linear quantity. So you cannot determine the power directly by using the superposition theorem. Right? So thank you very much. Right, so superposition theorem can be applied to the linear networks only. It means there is a linear relationship between the voltage and the current. It means if you increase the voltage, the current will increase. If you decrease the voltage, the current will decrease. So there is a linear relationship between the voltage and current. So this is the limitation of the superposition theorem, right? You can apply it only to the linear and bilateral network. Okay. Thank you.